All right, moving along here. Again, thanks for your patience and understanding. Our next speaker is Scott Starratt, and Scott is with USGS. The title of his talk is Sea Level and Climate Variability, Diatom Records from Coastal Marshes. As one of two paleontologists with the Volcano Hazards team, Scott works on marine, estuarine, and lacustrine ecosystems from Alaska to California. His primary research projects include using diatoms in sediment geochemistry to determine the magnitude and variability of freshwater flow into San Francisco Bay and climatically controlled moisture variations in Northern California and Nevada systems. Please join me in welcoming Scott.
Now can you hear me? A little bit better. I want to thank Dave and Life for inviting me to speak here, because what I work on is a little bit different than what most of the people in the room study. And I think since we have an issue of time, I'll start off with, are there any questions? Let's just dispense with the next 15 minutes. And my wife often says when I go to a party is if you really want to don't talk to anybody at the party, tell them what you really do. Tell them you're a paleontologist. So since I want to keep an audience, what I'll tell you is I'm a paleontologist. And then most people think Tyrannosaurus rex, and what I don't tell them is I actually look through the microscope. And the reason it's sort of important is what I'm going to try to convince you of is that you should look in a time frame beyond what rain gauges tell you about the climate, because there's an awful lot that we can learn even in what I, as a geologist or paleontologist, think of as the overburden or the recent time. Because sea level rise and fall has happened many, many times before. Sea level has been as much as 200 meters above what it is today in various parts. Denver was once under 1,000 feet of water, but that was a very long time ago. So anyway, just to sort of come up to speed with a little bit of what was talked about this morning by Dan Can and such. Sea level since the last glacial maximum was as much as 140 meters below what it is today, and this is just a modern reconstruction of how sea level has changed since that time. And about 10 to 12,000 years ago, marine waters began to enter San Francisco Bay, and the most recent iteration of San Francisco Bay began. There have been at least two other San Francisco Bays as we know them, based on paleontological and geological evidence. So about 5,000 years or so ago, there was a drastic change in the rate at which sea level rose. We finally had melted most of the glaciers that we were going to melt, and so the big input of water into the system had disappeared. You've already seen this graph. Dan showed it this morning, just to look at the record locally at Fort Point, and you can see that there's been a measurable change in average sea level rise even over the last 100 years. And you can also see that some of the major El Nino events have had an impact on short-term sea level rise. So why work with diatoms? Single-celled algae that will grow anywhere there's light and moisture. You can find them in soils. They've been found live on ice, on wires in the Arctic. So the point is they'll live just about anywhere. And from a paleontologist standpoint, they're great to work with because they secrete a very nice shell, which is made of amorphous silica. And the nice thing is that it preserves for long periods of time, long being millions of years. And in working in a marsh environment, it's not susceptible to the acidic conditions that often exist in marshes and destroy anything that's calcium carbonate. And so that sort of rules out the other commonly used microfossil in marshes, foraminifers, and to a lesser extent, ostracods. The other thing with diatoms is they exist in extremely high diversity. There are more than 600 species and varieties in San Francisco Bay alone. And in many cases, they're highly ecologically specific. Salinity, nutrient load, soil or sediment type, all will control what sorts of diatoms are growing in a particular place. The problem is, because they're silt sized, they tend to be transportable, they tend to be mixed up in the sediment through the process of bioturbation, and that high diversity and ecological specificity means that you actually have to spend time working with them. You have to be able to identify them, and you have to be able to understand what sorts of things control their distribution. Why use marshes? They tend to be relatively stable in longer term environments. They're better than, say, working in intertidal zones in San Francisco Bay, because those are subject to both biological and physical reworking, as well as human impacts, dredging and sediment loads and such. They're easily accessible. In most cases, you can either drive and walk to them or get in a kayak and get to them in that manner. So they're fairly easy to get around and collect material from. Problem is, in looking at marshes, is regional compatibility. Diatoms are diverse enough and different enough in different marshes along the West Coast that if you really want to understand what's happening in a marsh in the Nisqually Delta, then you have to go up to the Nisqually Delta and study the modern conditions. You can't take what you know from San Francisco on up to the marshes in points either further north or further south. Now, when we look at the record that's preserved in the marsh, there's several things we have to consider. There's the original inputs, which are going to vary depending both where you are located in the marsh. Are you on the marine end of the marsh, or are you on the freshwater end of a marsh in an estuary? That's going to control what sorts of species show up in the record. You also have to worry about what's getting washed in from the grounds surrounding a marsh environment. And because we're looking at a dynamic, tidally controlled environment, you have to worry about things that are reworked. And the problem with a marsh is that they can be reworked in an estuary, both upstream and downstream. So you can actually get transported marine species as well as fresh water. In a single place, you'll find variation in seasonality has an impact. In a Mediterranean climate such as Central California, the spring is quite a bit wetter than the summer, and so that has an impact on the amount of fresh water coming through the system and on the individual diatoms that will live in a marsh at a particular time of year. In looking at a longer term record, we can start, for example, in this illustration, we're looking at just a gradual sea level rise and assuming nothing else is happening within the system. There are no tectonic influences, there are no climatic influences, and sea level rising is going from the left to the right. So at the bottom, we have less, at this particular site, the water's fresher, the ocean hasn't had as much of an impact, and gradually over time, as sea level rises, there's an increasing amount of salinity in the water, and therefore we get a change in the flora. At the bottom, we have a more freshwater dominated flora. At the top, it's more marine dominated. We always have to deal with the reworked component, and we have to deal with what's being washed in locally. We can throw climate into the mix, and fitted on top of that very gradual sea level rise, the darker line shows you that we may actually change the assemblage based on climate. If there's more fresh water coming in at a particular time, you'll get a fresher flora. If there's more marine influence, because there's less fresh water, you'll get a more marine influence. So it's a little bit more complicated than just the straight sea level rise. In San Francisco Bay itself, some of the first work with diatoms was done by Rich Laws at Berkeley for his dissertation. And using multivariate statistics, he had laid out a number of different floras within San Francisco Bay itself, but he wasn't really looking at process. He was looking at just trying to lay out what the distribution was. He did apply it in identifying Sangamon or stage 5, the most recent major interglacial period sediments in San Francisco Bay, and helped to sort of map out the distribution of those sediments. And he was also able to apply them to looking at fault offset studies in what was known as the Southern Crossing from the East Bay to southern San Francisco. In doing sea level constructions, you can either look at it from a quantitative standpoint or a qualitative standpoint. And what I'm going to do is sort of walk you through the process of doing the quantitative kind of reconstruction. And the problem is, not a lot of that kind of work has been done in this country. Some of the best quantitative sea level studies have been done in marshes in England. So the process is you select a marsh and you run a transect from the intertidal zone up to a part of the marsh where the ocean doesn't have any more influence. Take a number of surface samples. You can sometimes do that over a period of time to get a seasonal view of what's happening with the individual flora. And then at some point, you take a core or cores to get a temporal idea of what's happened with the marsh. So the first step is to evaluate the diatom flora in association with particular water conditions. In this particular example, they looked at mudflats, they looked at high water stands, they looked at the highest astronomical tides, and characterized the flora just by the species that are there. But most people don't like to speak Latin, and so it's a lot easier if we start talking about things like ecology. And so you do the same sort of thing, but you think about it in terms of what do those individual species represent, and you start looking at changes across the marsh in terms of environmental conditions. Then you take it down core. You change from a spatial relationship to a temporal relationship, choose one point and go down. And so in this case, we followed through the same set of steps. We're now looking at the species down core. We do the same thing with environments. And you ultimately end up being able to trace out in this particular site how sea level has risen or fallen. In San Francisco Bay itself, we know the controls are the Aleutian low and the subtropical high. And just a couple of examples of how those have had very strong influences. 1977, one of the worst droughts in the 20th century, if not the worst. We had for a long period of time a high pressure system sitting over California, and the Aleutian low was way out to the west. During the El Nino of 82, 83, 97, 98, the opposite was true. The Aleutian low was sitting fairly close, and we got all kinds of moisture. So in order to do this study, I took calibration sites around the bay, took 3 downhole sites, the sites that are in white dots, to look at 3 different environments, and analyzed the diatoms. One of the problems is finding sites in the Bay Area that have sufficient long-term records. Most of them have been destroyed over time. So these are some of the few sites that actually have a surface record of current tidal marsh that goes down several thousand years. So we go through and we create figures such as this showing the different species, and in this case the abundance of freshwater species and how they vary over the last 3,000 years. Another example using brackish and marine taxa, and then start comparing different marshes. And the thing that you can see in colors here are the red or the pinkish colors are representative areas that have more marine influences and might be related to drier periods of time. The areas in blue are those that are a little bit wetter, and what you see is that the pattern is somewhat similar, however it's different in individual marshes, and that's largely due to local influence. Petaluma Marsh is largely controlled by its own watershed. Benicia State Park is probably strongly influenced by its location on the main channel of the Sacramento River, and Rush Ranch is sort of a situation that sits somewhere in between. We can also make comparisons to sort of ground truth, what we do by using other proxies. This is a salinity curve reconstruction from blue oak tree rings in the Central Valley, and it sort of shows that as salinity goes up in this reconstruction, the abundance of freshwater diatoms goes down, which is what you would hope. A couple of lake records. Mono Lake, particularly during the Little Ice Age, matches very nicely. Pyramid Lake does the same thing during the Little Ice Age. As the salinity of Pyramid Lake goes up, the number of freshwater diatoms in San Francisco Bay go down. And the black curve is from Ed Cook's PDSI drought paper that came out in 2004. And one of the big differences we sort of see is that San Francisco Bay does maybe a little bit better job of following the overall drought trends than Pyramid Lake does. And possibly one of the reasons is that Pyramid Lake it comes from a fairly small watershed. And if it's not raining or snowing in the Tahoe Basin, Pyramid Lake doesn't get any water. So in conclusion, we can actually get some climate signals out of marsh ecosystems, but we need to have an extensive knowledge of the biology of the diatoms that occur regionally to be able to take that record down core. Future research, we need to do more calibrations in San Francisco Bay, more detailed calibrations. That would allow us to do more down core studies, and these methods can also be applied to the modern marsh restoration projects that are taking place to look at how the system evolves over a relatively short period of time. And a word from our sponsor, another dull, boring climate meeting in the West, which is coming up in April. If any of you are interested, see me at this meeting or email me, and I can send you the appropriate information.